Again, welcome to the Banauliwood film city. I am fake Newton and fake Galileo, traveling in the Banauliwood film city developed by Mr. Prasad Gupta of Banauli village. And today, with traveling, I am going to discuss about the equivalency of inertial frames. So first, see the statement of equivalency of inertial frames. Same physical quantity is found to have different values when measured by observers in different reference frames. But the relationship between various measured quantities are found to be the same by the observers in different frames of reference moving with uniform velocity with respect to one another, or a frame of reference with unaccelerated motion. This means that the basic laws of physics are identical in all inertial reference frames, or that all inertial reference frame of reference are equivalent for the measurement of physical event. And this is also known as the hypothesis of Galilean invariance. Now, let's see this with an example. So, consider B and B dax are two inertial reference frames. B dax is moving with uniform velocity b relative to b. The space and times coordinate of an event and measured by an observer sitting in the frame b is x, y, z and t, and those as measured by the observer in b dash is given by x dash, y dash, z dash and t dash. The event is represented by p and p dash in both frame, and now we wish to find relationship between this coordinate, and experiments show that times read in b dash are equal to times read in b. That is, we can write t equals to t dash. For example, we consider initially both frames were coinciding at O. That is, O and O dash is coinciding when we calculated the time. We start to calculate the time, and after time t, B dash frame reaches at O dash with a velocity v. So, for the sake of simplicity, consider the axis of y dash, x dash, y dash, z dash of b dash parallel to the x, y, z axis of b, and also v is parallel, that is the velocity of b dash frame is parallel to x and x dash axis. Now let us agree to count time from the instant at which the two origins of coordinate y and y dash momentarily coincide, as we have discussed earlier. Then the coordinate O dash of B dash as measured by an observer in B will be x equals to Vt, y equals to 0 and z equals to 0. And the coordinate x dash, y dash, z dash, t dash of the an event measured from B are related to the coordinate x, y, z, t of the same event at measured from b by the following given equation: t equals to t dash, x equals to x dash plus v into t dash, y equals to y dash, and z equals to z dash as shown in figure 2. And these equations are known as the Newtonian or Galilean transformations. Now we can formulate rule for the velocity addition from these equations. Consider a particle has a velocity component u sub x as measured from b and u sub x dash as measured from b dash. Now we can write ux equals to x by t equals to x dash plus vt divided by t, or ux equals to x dash plus v into t dash divided by t dash equals to x dash by t dash plus v, or equals to u sub x dash plus v as shown in figure 3. So we can write u sub x equals to u sub x dash plus b as given by figure 4, and this can be written in the vector form u vector equals to u dash vector plus v vector. Where u vector is the velocity of the particle measured in b frame, and u dash vector is the velocity measured in b dash frame, and v vector is the relative velocity of the two reference frame, that is velocity of b dash frame with respect to b frame. Now the above expression, it follows that delta u vector equals to delta u dash vector as shown in this figure. Delta u vector is given by figure 6. Delta u vector equal to delta u dash vector, because v vector is constant, so delta v vector will be equals to 0. That is, we can say that the velocity change observed from frame b is equal to the velocity change observed from b dash frame. All the velocities themselves are different. Further again, consider a vector and a dash vector are the acceleration of the particle as observed from frame b and frame b dash. Then we can write a vector equals to delta u vector by delta t equals to delta u dash vector by delta t dash equals to a dash vector. That is, a vector equals to a dash vector, because since delta u vector is equal to delta u dash and delta t equals to delta t dash. Now consider m be the mass of the particle and f vector and f dash vector are the force experienced by the particle as observed from the frame of reference b and b dash respectively. Then we can write f equals to m into a vector equals to m into a dash vector, because we have calculated a equals to a dash vector. So we can write f vector equals to f dash vector. We can see it from this figure. Here Figure 8 represents this relation. Figure 7 represents the relation between A vector and A dash vector, and figure 8 represents the relation between F vector and F dash vector. So we can say that these two forces are equal. Thus we conclude that although the particle appears to have different velocities to observer in different inertial frames, the force experienced by the particle as computed by different observer is same. Similarly, if observers in different inertial frames measure the momenta of the colliding particle, they will obtain different numerical values, but each will find that the total momentum of the system remains the same after collision as it was before. That is, the law of conservation of momentum holds good in all the inertial reference frames. So with this, I would like to end this lecture here, and for your great information, I would like to tell you that these all videos are financed by, or these movies are financed by fashionable film city Banauliwood movie developers. So let's support these videos to